Welcome to PreCalculus Section 8.6 Partial Fraction Decomposition Part 2 of our lecture. We're going to do a few more examples here. So on the next example, the first thing I'm going to do is factor my denominator. So I have a GCF of x squared. So that gives me x squared times x plus 1. So rewriting my fraction, I have this fraction here. So I'm going to represent this as a sum of three partial fractions. So the first one's going to have an x in the denominator, the second one an x squared, and the third one an x plus 1. So the reason I have three fractions this time is because I have a multiplicity on the linear factor x. So it's got a multiplicity of 2. Alright, since it has a multiplicity of 2, I want to write the first power and also the second power right here. Alright, so I've got to represent both of those. When you have a multiplicity, you want to go up to the highest number here, which is 2. So you have an x to the 1 and an x to the 2. Alright, so I need both of those. Now let me remind you back on a previous slide, right here, where I pointed out this thing that confuses people at the beginning of learning how to do this. Even though x squared appears to be a quadratic factor, it's really your linear factor x with a multiplicity of 2, which takes a constant on both the x and the x squared. So let's put our numerators in. So this one a, then b, then all of these are linear factors, so this one would also have a c. So now we can go ahead and get a common denominator. So let's set that up. So I set that up so I can see that I need to multiply by these forms of 1 here in order to get the denominators to all be x squared times x plus 1. Okay, so now let's simplify that another time. So I wrote all of that out, and I distributed this ax times x plus 1 here, this b times x plus 1 here, and the cx squared here. As you can see, there's common denominators across the board. So now we can combine all of this into one numerator over one of these as the denominator. So let's do that. So I have all of the numerators set up over one of the denominators. So now what I want to do is to set up an equation using the numerators on both sides. So let's set that up. So let's move this up a little here. So we've got that all written out now. So now we can see here that we've got an a and a b and a c. So that's three variables that are unknown. So in order to find three unknowns, we need a system of three equations. All right, so let's highlight our coefficients to set up our three equations. So for the x squared coefficients, I have a 14, an a, and a c. And then for the coefficients of x, I have a 25, an a, and a b. And then for the constant, I have a 5 and a b. All right, so let's write our system of equations now. So we've got, let's move this up a little bit. All right, so we've got 14 is equal to a plus c, and 25 is equal to a plus b, and 5 is equal to b. So we've got a system of three equations with three unknowns. All right, so we already know b. We can see that's right here. So now we can use elimination to to eliminate a from the first two equations. So let's multiply one of them by a negative. So I'll get negative 14 is equal to negative a minus c. So let's go ahead and take that equation and add it to the second equation to eliminate a. So I wrote those two equations down. Now the a's are eliminated and we're left with, let's see, 11 is equal to b minus c. And then from the above system we have b is equal to 5, so we can say 11 is equal to 5 minus c, or 11 minus 5, that's 6. 6 is equal to minus c, so that would be c is equal to 6. So we know c is equal to 6. Let's just write that b is equal to 5 as well. So we know both of those so far. Whoops, we forgot our negative on the 6 here. Let's put that there. So we still need a, so let's go back up and find an equation for a to substitute in up above here. So we could use this one here. So we can say now that 25 is equal to a plus b. We know b is 5, right? So a plus 5, so that's a is equal to 25 minus 5. So that would mean a must be 20. All right, so we have a, b, and c now. So now we just have to put those over the right partial fraction and to get our final result. So going back up to the top here, we're going to figure that out. So you have to be careful you put it over the same one. So a goes over the x, so that's 20 over the x. And then b goes over the x squared, so that's 5 over the x squared. So c would have to go over the x plus 1. And then we usually write this with one sign here in between. So now this would be our partial fraction decomposition. Now you could always, if this doesn't seem likely to you in your mind, you could always go back and add these fractions together using our methods that we use for finding common denominators and adding fractions, and you could verify that you get back to this right here. All right. All right, find the partial fraction decomposition of this one here. So first step, factor the denominator. So when you factor x squared minus 16, that's a difference of two perfect squares. So you get x minus 4 times x plus 4 in the denominator. So we'll set that up. So we've got, 6x plus 40 over x minus 4 times x plus 4. So that's going to be equal something over x minus 4 plus something over x plus 4. Linear factors of multiplicity 1. So those will take a constant in the numerator, so we use two different constants. All right, this is our setup. So now let's go ahead and find common denominators on the right so we can combine the right into one fraction. So I'm going to multiply my first fraction by this form of 1 and my second fraction by this form of 1 to get the constant, the common denominator, correct? All right, so now let's write this out. So I wrote all that out, and I did the distributing here and here. So now you can see we can add these two fractions together and put it over one denominator. So there's that. And now, since we are ready to set up our final equation, we take our numerator and we set those equal to each other. So there is our equation. All right, so now we're ready to highlight our coefficients so we can set up our system of equations. Since there are two unknowns, A and B, we should have a 2 by 2 system of linear equations to solve. So let's see. So let's make our coefficients of the x here and here one color. That's one equation. And our constants another color. And we'll set up our system of equations. So we've got 6 is equal to A plus B. We have 40 is equal to 4A minus 4B. So we have a 2 by 2 system of linear equations. Let's solve this using the substitution method. So from the first equation, I can solve for either A or B. So let's just say A is equal to 6 minus B. And then substitute for A in the second equation. And solve the second equation for B. So this is 24 minus 4B minus 4B. 16 is equal to negative 8B. So B is going to be negative 2. Now go back to this equation and substitute for B. So we'll have A is equal to 6 minus negative 2, which is 6 plus 2. So A must be 8. All right, now we go back to the original equation to figure out which gets the A and which gets the B. So the x minus 4 gets the A, and the x plus 4 gets the B. So A goes with the minus. All right, so our final partial fraction decomposition is 8 over x minus 4 plus negative 2 over x plus 4. Of course, we usually write this as one sign here. So this would be your final answer here. Now let me just point out that there are other ways that this could be written. So if you put it in this order with the x plus 4 term first, you'd have to carry the negative with the 2. You could also write it in this order, like this. Either way. Our final example here. So I'm going to decide whether these are irreducible factors in the denominator. This clearly can't be factored. Now if you tried to factor x squared plus 3x plus 3, you could prove to yourself that it's not factorable. So this is considered an irreducible quadratic factor. So let's set this up. So I've got this set up here. Now we have to decide what our numerators are going to look like. Now let's go back to the slide where I talked about the form of an irreducible quadratic factor in the numerator. So here, it's this case here, where if you have an irreducible quadratic factor similar to this here, you've got a linear equation, a linear expression bx plus c that you have in your numerator. So for the linear factor x minus 4, we just have a constant. And then for the irreducible quadratic factor, we have a linear expression bx plus c. So we have 3 unknowns that we need to solve for in this problem. All right, so let's go ahead and combine our 2 fractions on the right into one fraction by finding a common denominator. So I set that up. So now let's go ahead and carry out the multiplication in the numerators here and here. All over these here would be our common denominator. So let's set that up. So there it is. I set that up. I carried out the distributing here and the double distributing here. All right, so now I'm ready to combine these two fractions into one fraction. So I wrote it all out. So now we can see that the numerators have to be equivalent. So we'll set up an equation using only the numerators. All right, so I wrote that out. Now let's go ahead and highlight the coefficients of the x squared, the x, and the constant terms in different colors. So let's start with the x squared terms. So the coefficient here is 5a plus b. All right, and then for the x terms, I've got a -1, got a 3a here, a -4b, and a c. And then for the constant, -14, 3a, and -4c. So let's set up our 3x3 system of equations. Let's scoot this up. So I've got 5 is equal to a plus b. -1 is equal to 3a minus 4b plus c. And I've got -14 is equal to 3a minus 4c. So this is our 3x3 system of linear equations that we're going to solve. So there's multiple ways that you can solve these systems. So what's occurring to me first is I'm going to solve the system using elimination, and I'm going to try to eliminate the 3a from this equation first. So let's multiply this equation by -1, and I'll get 1 is equal to -3a plus 4b minus c. So I'll take that equation and I'm going to add it to the last equation. I'm going to eliminate my a. So I wrote those two equations down. So I'm going to solve these two by eliminating the a terms. So that's -13 is equal to, let's see, 4b minus, so that's -1 minus 4, so that's minus 5c. So I used the second two equations to come up with this equation in terms of b and c. Now let's go ahead and use the first two equations to eliminate the a in this equation, and then we can solve for b and c using the two equations that we come up with. So that would mean I would multiply this equation by -3, and then I'd get -15 is equal to -3a minus 3b. All right, so I'm going to write that equation down. And I'm going to write the third equation down. Not the third, the second equation down. And I'm going to solve these two. The a's are going to eliminate again, so I've got -16 is equal to -7b plus c. So what I've achieved is two equations in terms of b and c now. So I should be able to solve those two equations simultaneously to find b and c. So what I did here was I took this equation here and this equation here, and I made this 2x2 system of equations here, which I'm going to use to solve for B and C. All right, so let's scoot this over a little bit. So now let's eliminate the C here by multiplying by positive 5, which will give me, see if I can make enough room here, which will give me negative 80. I don't have enough room. I'll have to go, let's go down here. I'll have negative 80 minus 35b plus 5c. All right, so now I'll add that to the top one. Oops. Let's fix this. We have an equals here. Negative 13 equals 4b minus 5c. All right, so eliminate the c, and we're left with negative 93 is equal to negative 31b. B is equal to divide, so you get 3. Okay, so we have a B now. So now let's go back over to this equation where we can put in that 3 right here and solve for C. So let's do that in green. So that's negative 16 is equal to negative 21 plus C. Negative 16 plus 21 is 5. So C is equal to 5. So now we just need A. So let's scoot over a little bit here. So we've got, where's an A? We need an equation with an A. So let's go back up to, all right, so here's one up here. Let's go back up to this one here, which is 5 is equal to A plus B. Let me write it down here. So we can substitute B in there, which we said was 3. All right, so A is equal to 5 minus 3. So A is equal to 2. All right, so let's write that on another page so we have some room to wrap it up. So there it is. A is 2, B is 3, C is 5. Now we need our original setup up top here. So we need A over the x minus 4 and bx plus c over the x squared plus 3x plus 3. So let's write that on our new page. So there's our setup. Now we'll just plug in our constants. So 2 over the x minus 4. B is 3. C is 5. X squared plus 3x plus 3. So this is our system here. Not our system, but our two fractions, our partial fraction decomposition. So this is our answer right here. Our partial fraction decomposition of the original fraction that we were given. So this is the final result. So briefly, let's make sure you understand how to make your setups. So if you start with a denominator that has 2 linear factors in it, you've got 1 here plus 1 here. These take a constant in the numerator. If one of those linear factors has a multiplicity, then all of those multiplicities up to the highest has to be represented over here. So you've got the first power 1, and then the highest power being 2, you've got the second power 1. These are linear factors, so they get a constant in the numerator. So this is still considered a linear factor of multiplicity 2. It gets a constant in the numerator Of course, this is a linear factor, constant in the numerator. If it looks like this is a linear factor, linear, linear, constant, constant. All right, so then going down to here, this is a multiplicity of 2 on a linear factor, so you need to represent this x as an x and then an x squared. Both of those will take a constant in the numerator. This is a linear factor, constant in the numerator. Now down to here, linear factor. This is an irreducible quadratic factor. So the linear factor takes a constant in the numerator. The quadratic factor takes a linear expression, bx plus c, in the numerator. One more. If you have a linear factor and a quadratic factor of multiplicity 2, the linear factor takes a constant. The quadratic factor, both multiplicities, well, you have to represent all multiplicities. I don't know how else to better put that, but you'd have the 1 and then the 2. So you'd have the 1 with a linear expression in the numerator, and then you'd have the multiplicity 2, the highest multiplicity, with a linear expression in the numerator. All of these constants have to be different letters. Okay, I don't expect you're going to have to do anything like this other than perhaps decide the numerator. I think there might be one like that in the homework. All right. So you'll be solving 2x2 systems of linear equations and 3x3 systems of linear equations to find your constants. So I hope you took good notes and get started early on your problem sets. Let me know if you have any questions.